I'll continue with the molecular level modeling part and also say some of the things that Jörg couldn't get through first. You've seen we've discussed that DFT is not perfect in terms of describing the electronic properties of water. And we could calculate using a combination of tip-3P water and then for uncorrelated snapshot performing DFT calculations, different levels of DFT functionals in order to get the electrostatic potential. And this is just some of the snapshots that we've calculated. But when we average, then we can extract what is the position at the vacuum level, what is the valence band position, and we know what the band gap is. And then we see that PBE severely underestimates the band gap of water. And this is a problem because this is usually our workhorse for all the calculations. And that it can become a problem, we've mentioned it already, but I wanted to show you, this is here the valence band maximum distribution and conduction band minimum distribution of platinum 111 in contact with water. This is the water, and this is here the Fermi energy of the platinum 111 surface. And when you look, the PBE results are the green ones. That there is here, it is enhanced a bit. You see that there is an overlap between the Fermi energy of the metal and the valence band of water, which means that when we run our calculation, we actually get states that kind of so-called charge sloshing. So we go from one side of the Fermi energy to the other. So we have charge being transferred to the metal and then back to the water. And this actually leads to our calculations clashing. And what we were then forced to do is to, or not forced, but what we did is we performed calculations at the level of RPBE, which describes the platinum work function a little bit less good compared to experiment, but actually we avoided this kind of problem of charge sloshing. If we were able to do something, at the level of, for example, an HSE calculation, which is not perfect for other reasons, because we said we have there a mixing parameter, which is in principle something that is empirical, then we wouldn't face this kind of problem. But overall, I wanted to say we really need to be very careful and inspect our calculations in order to see that we are getting something that's reasonable. You also saw this kind of plot from Jörg, where we have kind of a band diagram. So here we have the metal, here we have our neon electrode that we discussed, here we have the water band gap. And when in principle, we can vary the field that we apply within the band gap of water up to a certain point. So as we apply a field, we have a tilting of the valence and the conduction band. And at some point, when the field becomes too high, we have that the valence band maximum, in this particular example, touches the Fermi energy of the metal. And this is the point at which we have the maximum field. If we continue increasing the field, what will happen is that any charge that we have here will go into this direction, and basically we pin our band state, so we pin the Fermi energy, so the valence band maximum. We can go also in the other direction with the field, but then at some point the conduction band minimum of water will dip under the Fermi level. So this means we do have some kind of, natural limit in our setup up to which we can vary the field.
Excuse me.
Yeah.
But of course, this depends on the fact that PBE underestimate the band gap.
Of course.
Because of course, if we had, I don't know, if HSC plus something, which reporting 10 or 9, the optical
we will
band
have
gap, then it would be absolutely correct that the charge goes in the opposite direction. So I think it's a problem just of the function, not of the setting.
Yain, not quite, because even there, I mean, there is a maximum to the field that you can apply, and this will be given again. I agree that PBE underestimates the band gap, and therefore we will much faster reach this limit, but even with HSE.
Yeah, in that case would be correct, because if you apply a bias which is as strong to be larger than the band gap, then is provided that you don't break the system with that bias, it would be all right that the electron transfer occur in that direction, because this is the pinning of the levels.
Even here, it doesn't have to be wrong that you get this, but this gives a limit to what we can do. Of course, this is what, when you start, let's say, evolving a reaction. But what I'll get in a second to the setup. Give me just a second, and I'll talk. So this is what happens. So basically, you start any additional charge that you apply on the neon in order to get the field will be then transferred, in this case, to the metal electrode, and you can't go further.
Okay, with your set, I see.
Yeah, and this will happen regardless of the functional that we have. It is just that if we have a functional that describes better the band gap, then the range within which we can vary, how much field we can apply will be higher.
Yeah, no, but I was thinking like my setting, which is the one typical of molecular electronics, where there is no transfer to the other electrode, but each electrode is connected to a reservoir with a certain electrochemical potential. So in that case, in this extreme case, you would really observe what happens in nature. I mean, that there is a pinning of the level to that electrode, and at some point when you apply sufficient bias, the electron transfer goes in the opposite direction locally, but not on the other side. But this is an extreme situation.
But I think we need always to ask ourselves, what do we want to model? So we would basically to reproduce or model the experiment.
Of course. I mean, it was not. It's absolutely fantastic. Yeah. It's not a critique.
And no, I didn't get it. But I think, ask me, because I think these are important things that we need to clarify. So what we have in experiment, just to remind, we have somewhere, an electrode, and we have here the working electrode, and experimentalists apply a bias. Jörg mentioned already that they don't do very. If you look what kind of changes they do, they don't seem to be very big in terms of what kind of bias they apply, but they have huge effect on the working electrode, and then we have these big fluctuations. Now, if we want to simulate a reaction, we need somehow to get the field that will maybe trigger this reaction there. The point is, if you think about water has bulk water has a dielectric constant of 80, which means that we do have here really a very big screening of the, the field that gets to of the potential, and the field that we get here at the electrode is screened. We also have, due to our setup, which we still think is quite good, but we do have here kind of a vacuum layer in between the neon and the water. And so if you have a vacuum layer, you have then a screening of 1, which means that a lot of our potential drop occurs actually at this interface. And this is something that if we could avoid it, if I could, I didn't have this large potential drop, then I would still have my screening of 80, but I will maybe get a higher field in here. So at this point, we lose kind of a lot of the potential that we apply. Stefan and Florian actually calculated this by running an extremely long water calculations. I don't know how many months they run it, and they see, if they apply a potential, they apply a voltage of 4.5 volts. What we get at the water working electrode interface is 0.7 volts. So you see, we have really a huge loss. So we need to do something about this.
Just to understand theoretically what you've done here, because we have 0.7 versus 4.5 with respect to what? Because I have in mind the Jun Chen operative method to align water bulk level to vacuum standard hydrogen electrode.
So at the moment, this is not really aligned to anything. This is just kind of we can calculate what kind of charge we have and what kind of potential we would, in principle, this potential will be the corresponding potential.
But then to align to the standard hydrogen electrode, you would add 444 to 4 to 0 now, which is now.
So you mean here?
Yeah, to align that.
I mean, if we take this, you can take this as an arbitrary point. So we can align it by using, doing calculation on a backside using the work function. You want to say?
Okay, so
I would really say one should not really, so this is not the point here.
Yeah.
So the point is really, so what is the electric field? That's the only physical observable quantity. So I want really to really describe it. So I would not, at this point, so one really has to set up then and ask, what experiment do I want to compare to? So what would be then the ion solution end at end? So this would be Poisson-Boltzmann, which one would have to apply in order really to put it then in reference then to, with respect to the voltage. So here the point is really just the question, so what is the charge at the interface, the average charge, and what is the electric field?
No, that's
I would not really...
That I understand, and my apologies, I jumped to another related question, but that I appreciate. I was just, since we were here and I thought, okay, how do I align that? But perhaps we can discuss
alignment is something
time.
I'm not discussing. So in principle, we know how to align. This can be done. But the point I want to drive in here that, yes, we have this setup which allows us, to have a potential drop and get the field, but what is actually the field that we get at the interface? And this is not so big. And so given that if you have here such a high voltage and you look at the setup before, that we do get to this breakup at some point, this means that we actually maybe cannot go so high with the fields that we can observe something simply because to our setup and constraints that we have in terms of functional, in terms of, losing a lot of the charge already here. And then one needs to be careful and one needs to check also the calculations, because whenever people have tried to apply these methods, and then for some, I've had now already 3 times the question, I put this in this field, but I don't see that anything happens. So what you need to do is to look at the layer resolved density of states, and then you can really see that on one side of your system you have the valence bed at one point, or the conduction point, and the other side it is here, so that they align.
No, it's
Sorry.
fantastic that you say that, because all of this is hidden normally in papers, and you are very generous in sharing all of this, because, and that is very crucial, and people should really, be aware of this and not apply methodologies in a blind way. And this it is true for every methodology we apply.
Yeah. Sure.
I'm just a little bit unclear about the physical situation. Are you saying that this voltage drop is unphysical, or it's physical but you'd like to work around it?
Yes, we would like to work around it. So
it's physical, but you want to work around that will allow you to make.
So this is something that is coming at the moment due to our setup, that we lose a lot of this kind of. We have here a huge voltage drop within this region. And this is a region which is, in a way, a computational setup which allows us to charge the system and get an electric field in there. But if I didn't have any voltage drop here, it will be better, because then I could get a much higher field on this side where I'm interested in having it.
And the structure of that's a first layer of water there, right? Where the voltage has a big...
Yes.
That first layer of water is completely aligned, or how would you characterize
it? It is not completely aligned. I have later on a structure from the MD. It comes at some point. I didn't put it here where you can see. We do have some alignment there, but actually the neon seems to be rather gentle, I would say, as compared to something like platinum, where you do see a very strong structuring. I think any time you place kind of even a hard wall on water, there will be a little bit of structuring, but the point is how big it is. Yes.
Thank you. This might be a naive question. So I wonder, what is the mechanism for this drop? Is it because near the boundary, the orientation of this, or the of the water is restricted by the boundary or something else?
No, the drop is actually really due to us having here a hydrophobic gap. So there is a little bit, let's say, space between the neon and the water, and this is like having a vacuum region. So if you remember, I don't have now the picture here, Jörg was discussing this, the dielectric constant of water as you go to confined systems. And the smaller, you went, the smaller the dielectric constant was. So this was this kind of plot which also experimentalists had measured, where they have, here is somewhere the bulk dielectric constant, and then you had something like this, and here it was around 2. Yeah, and here was 80.
So just to confirm my understanding, so it's not about the orientation of the water molecule near the boundary, but it's because of this vacuum or the hydrophobic layer.
Yes.
So if that is true, then I wonder if we can modify the boundary to hydrophilic. Would that help? We can try, but then you have something which interacts with the water, and you don't want to have something that interacts with the water. I will show a solution that we have kind of come up with, how one can bring it a little bit closer. But so it's good that you ask. Please continue. Yeah, so if we have something hydrophilic, then this will mean that it will interact with the interface. Okay.
Yeah, and then you will kind of not have something on this side that is just a spectator and helps you to modify your system in a way that the working electrode that you're interested in has the properties that you want, so that you get here a charge. But actually, this will be something that you will have also to consider in your setup, because this will interact with the water.
I find the idea very interesting, but you have also to remember, so this has to be a semiconductor, and a wide bandgap semiconductor, and a closed shell system. So this really makes it very, from the nature, very hydrophilic, because there is no interaction. And what we typically find, even for magnesium, which is super reactive, the gap is still rather large there. So there are a few water molecules that are that are chemisorbed, so which do it, but you don't really get then a close contact between the water. And then it's simply a matter then of numbers. So you have then 80, which is the dielectric constants in water, and 1 in the vacuum region, in this hydrophobic gap. So if you have now in water a distance of 80, you lose the same voltage in 1 or so. If you have 1 angstrom to 80 angstrom, so it's a gigantic drop that you're having there. That makes it so complicated.
Yeah. So we are not the only ones who have made some suggestions, on how to charge or get charge on the working electrode, and there are a number of examples out there. So I would say one of the first who did something were Lozovoy and Alavi, who had they looked not at electrochemical system, but actually in systems in vacuum, but they used a sheet charge and then have a gallium kind of screening. And then you have also symmetric slab, so this is the limitation. Matilde suggested at some point this ion imbalance method, where you do what the real system would do, that you have, for example, sodium and chlorine ions in there, but you don't have the same amount of chlorine and sodium atoms, so that you will naturally have a charge transfer in one or the other direction. The problem with this approach is that while it will mimic kind of really the electrochemical system, you're always bound to having discrete jumps of electrons, and you cannot apply really a potentiostat in the way that we can do it, because we want to have a fine-grained way in order to change the electrode potential. Then the method by Otani, Jörg mentioned at some point, where he really transfers electrons in a real way, but this is difficult for DFT system, and he has coupled it with the rhythm approach. So this is a Green's function-based approach in order to have kind of the surrogate model. Then there is VASP-Sol, which is a continuum solvent with a countercharge, and I guess Richard will talk about VASP-Sol in the afternoon, probably. I don't know when his talk is. And then there are various approaches which use a continuum solvent and a countercharge. So here are 2 examples. Now, our example was with the computational counter electrode, and what Christoph Freisel did is to extend the dipole correction to include also a monopole. So this is then the so-called generalist dipole correction, and this can be used in order also to do charging. And he's using a lot in order to study kind of atom probe tomography setups. But the challenges are always, how the countercharge in all of this is outside the water region. So in any case, you will have such a kind of vacuum region, which may limit how much charge you get. Then how do you get a coupling to the thermostat? It doesn't work with all these approaches. And then, of course, one has to have a measure to the reference potential, but then this can be done. Now, we tried to put this together a little bit and classify it in terms of techniques that we have. And what you see here is the setup. So you always have somehow 2 electrodes or 2 electrons and the water sandwich in between. This will be the potential that you will see. And this is the charge that you apply. Now, when you have a gallium background, this is mirrored out over the whole cell. And if you look at the potential, you have a parabolic dependence here. If you have something where you have 2 d-periodic boundary conditions, which is the applying to the case of Otani's methods, where he simply in one direction removed the the periodic boundary conditions, then you have such a potential drop, so one that we would be actually interested in, but you have a non-neutral supercell. There is the approach that comes from the modern theory of polarization, where they can apply fields, but this is working only for semiconductors. If one uses an implicit solvent, then one has a restriction of the potential drop to the region close to the electrodes, and this is so you get in the middle kind of a flat region, which means that the potential doesn't change. And then you have here either some kind of QMMM methods where you have a quantum mechanical region and then you couple it to some kind of implicit solvent, for example, or a force field. And this will be, so you have here the quantum mechanical region where you would like to describe it with DFT. Then here you have molecular, what is it, MM is, I always forget the abbreviation. Anyway, you put a force field or an implicit solvent here, and then you can have here a vacuum region, and you can see that you have here kind of a counter charge, or this explicit counter ions that have been used, but these are difficult to get potential control in. Now, this is the method that we proposed and discussed so far with the neon electrode. And given the difficulties that we discussed, that having the electrode outside of water and then having this vacuum region that we would not like to have, we thought, okay, why can't we bring the electrode closer to our, within the water region by not using maybe an explicit neon layer like we do here, but maybe some kind of Gaussian charge distribution or something that we can bring closer by. What would this mean in terms of now this picture that I showed before with the maximum electric field? So basically the idea is we bring our electrode closer so that we have here the potential drop that we would like to have. This will be still screened by water. Water has this dielectric constant of 80. But if we can bring our electrode closer to the interface that we are interested in, we can, despite the screening by water, we can get a higher potential drop at the interface. This has a further advantage that here afterwards, because we have the potential drop here and here, we will have really a flat potential region already within our
water film. And what we could do is to give this this kind of charge distribution also properties that will simulate the whole double layer afterwards. So that's the idea. Then it would look such that we do have here our electrode, we have here our fully solvated countercharge, and then we have also the valence band and conduction band of water flat in this region, and this would be whatever the vacuum neon. And you can see that, of course, we need to be careful that we don't bring this charge too close, so we still want to have this very high potential drop at the interface that we have in the real physical system, but we can achieve a much higher field at the interface and therefore also look at reaction or things we can't look at the moment. And this is from, this is how it would look like. So this is the potential drop. You see, we still have here those oscillations that we had discussed before with the DFT systems that are close to the interface. We have here this an electric field, and we do see that we do have here a region that is flat, kind of in water. Of course, close to the electrode and to the confining wall. I will talk about this in a moment. We do have some structuring, but we do have here a region that is really bulk like water. Now, one thing that the neon did was to confine our water on one side. So you saw when we did the hackathon, if we didn't put any confinement, the water kind of ran around. This was also because we didn't have enough water, so we couldn't kind of keep it together. But what is very nice about the neon and having something that confines your water is that your surface dipole of water is actually not so high. So if you have just look at the water surface, there are in each snapshot, there are kind of really waves. Like Jörg always says, you look at the ocean, and then if you're at the beach, you see that there are big waves. If you look on average, you see that something is flat. And this is also what happens. So the surface dipole of water, if you look at any kind of screenshot, there are really this kind of waves. And you need very long trajectories in order to equilibrate this. So this is in the order of nanoseconds and definitely not something that we can do in DFT. Also, if you look at the surface dipole of pristine, of a neat water surface, this is in the order of 0.3 eV, which is not small. And this means in a setup like we have it here, where we have, a pristine water surface, we need to consider this kind of 0.3 V in addition to this, what we have here, in order to describe our whole system. We find that if we put neon or any kind of confining wall here that really confines a little bit the fluctuations of the water molecules at the surface, we get this surface dipole becomes much smaller. So we are talking then 10 MeV in the order of magnitude. So basically, we are from 0.3 to 10 MeV, 0.3 eV to 10 MeV. This is really a big difference. And so we would like to have something that ensures that our water, first of all, doesn't fly away into the vacuum, but also has then a surface dipole that is smaller. And for this, in this region, we put now kind of a mechanical confinement potential, which keeps our water molecules here. So we have here a fully solvated countercharge, which allows us to charge the working electrode, and we have here a confining potential, which ensures that we have a small surface dipole and also that our water doesn't kind of fly away. Sorry, I have here something that I need to cancel because some permission is asked. I don't know. Okay. So, and we did calculation with this already in LEMS. We can do rather long ones and also tried it with DFT. Now, now we have Jörg discussed the potentiostat, we discussed the electrodes, we discussed the dielectric breakthrough, and also I had shown this, we had shown both this kind of example of magnesium corrosion and dissolution. And I think we need this level of realism, otherwise we will not be able to kind of model a reaction like this. But this also involves kind of a workflow that is not always very straightforward, and it took us a longer time to really figure out all the steps. So first of all, we create our geometry of the half cell, and we had some experience with this in the hackathon. So we can put here any surface that we want. Then we need to ensure that we have the water structure, that it has the correct density in the bulk-like region, that it is space-filling. Then, for this, usually we use Python. Then we need, you remember probably that we set up our water structure by just putting water molecules in a simple cubic arrangement, which is obviously not a water structure. So we need to pre-equilibrate it. And this we do at the level of some kind of tip 3P water typically. And then this is, we need to have the potentiostat. This is where we do the DFT calculations. And then, of course, we need also to have analysis of all the steps that we have, visualization and so on. And you can see that this requires kind of really this complex simulation protocols, but it's very easy now to set them up using Pyron, and then this is what we do. Of course, you can do it also without this, but it is extremely convenient, in particular, for example, this step here where we go from tip 3P water to DFT water, where we just kind of change one line and say not use LEMS, but use VASP, something like this. Now, I would like now to talk about a specific example in order to discuss a bit the build above the double layer, and we found this particularly interesting. And we looked at hydrogen absorption of platinum. Now, first, when we did our our setup with the thermopotentiostat, and we did it for magnesium, but people were always asking for platinum because this is like the fruit fly system for electrochemistry. There are a lot of experimental and also theoretical work. And one can compare things. And initially I thought there is so much work for platinum. Is there anything else to be learned there? But it turned out to be quite interesting. Now, very briefly, what you're seeing here is a CV curve, where on one side you have the current that is measured, and this is the change of the electrode potentials. And CV curves usually look something like this. So you have here a region where, for platinum, you have hydrogen absorption, desorption. Then here is a region where it's kind of getting flat. So this is the region of where you don't think that you don't have any specific absorption at the surface. And then this is a region where you start to have, this is moving quite a lot. So you have kind of oxidation. Okay, I do have here something on my screens, which I don't know whether this console. Okay, sorry. Not sure where this was blocking it. Anyway, what is very nice about this CV for platinum, and that you see that it's completely, okay, now I don't see the pointer at all. Okay, here, yeah, okay. Yeah, so it is completely symmetric, which means that going in one direction and going in the other direction, this is all governed by thermodynamics, so I don't have kinetic effects. It's completely reversible. And what we were particularly interested in is this kind of region where we have on one side hydrogen desorption, and on this side we have hydrogen absorption on the surface. And what was interesting, that there seems to be a maximum coverage of hydrogen that can be reached at the surface. This is around 0.6 monolayer, and afterwards they see that there is hydrogen evolution reaction onset. Now, if you do not consider water, you get even much more hydrogen on the surface, up to 1 monolayer. So probably the presence of water has to do something with this kind of limiting coverage, but it wasn't clear what it is. And at the time, a lot of the calculations were performed with vacuum.
They actually have done this kind of calculations with water. And they was able to observe more than 0.66. But the very interesting thing is that you know that there are these two kinds of hydrogen over the surface. The hydrogen under-deposited hydrogen, which is absorbing on FCC side, a hollow side, and over-potential deposited hydrogen, which is absorbed on top. And with this calculation with water and hydrogen on very big system with counter ions, I observed these two species. And the very interesting thing is that the hydrogen of one species, when they hit the 0.66, let's say that the top configuration, the overpotential deposited, then they start desorbing, that is metastable, then they start desorbing, but this is consistent with having additional coverage on the surface on LCC positions. So I don't know why that is different from what you observed. One possibility could be that there are ions in solution that could screen a little bit, so give a little bit.
So maybe I will discuss this, what we see.
I don't know. Anyway,
and one can get further. The point is that this is kind of the, this is the limit. And I'll get to this, why. Now, what we wanted to do, so now we did it without applying any potential, is we can look at the work function, or this will be equivalent to the electrode potential. What we do here, we align, so my 0 is the work function of the pristine platinum in 111 in vacuum. So this is, I just say pristine platinum in vacuum is my 0 point. And when I start putting in hydrogen in different coverage, so increasing the coverage up to 1 monolayer, which means that all the possible sites on the surface are occupied by hydrogen, and I have the ratio of hydrogen to platinum in the first layer is exactly equivalent. And I see that when I do the calculations for vacuum, I have here this change in the work function, and this very closely follows to what we have from experiment. And it's also not very astonishing because we know that the work function is described quite well in DFT. So basically what I have here in a schematic picture, I have my electrode. I always have, when I create a surface, I have a certain spill out of electronic charge. So this gives the surface dipole. And then when I absorb hydrogen, I have here a change in the kind of a potential drop at the surface. Now, this is experimental data, which is taken and again aligned to this region. We see that we do have very similar kind of behavior. If I simply move this line up, I see that I almost follow the same have the same behavior as in vacuum. But I do seem to have here a drop. So if I put water, if this is at 0, this is at 0.6 or 0.7. So only the presence of the water kind of shifts the potential drop, but otherwise the curves are very similar. So what does the water do? I mean, is this its only purpose? What we did then is perform calculations where we start putting in, we have the platinum surface in contact with water, and then we start putting hydrogen at different coverages at the surface. And so this is the green curve that you see here. And you see we follow quite nicely the experimental curves for the point that we have calculated. You also see that at this point, we have kind of a reversal of the slope. And when we go to 1 monolayer, we actually are very close to the value that we would have in vacuum, so if we didn't have any kind of water around. Also within this region where the behavior changes, you see that we do have kind of this dashed line to indicate that something is changing. what we also see is, so let us kind of try to understand what is going on. First of all, we have our platinum surface. We put it in contact with water, and of course the water at the interface will reorient in order to screen this potential drop that we have at the interface. And this is what gives rise to this kind of shift that we have in the work function. As we start putting hydrogen, so this is then here this potential drop that we have. If we start now putting hydrogen in there, what will happen is that we have additional charges here, so this will change somehow the potential drop, so it will become bigger, and this will give rise then to this point here. We continue increasing the coverage, and this will slightly modify here the potential drop that we have here up to a certain point. Now, after this point, when we start putting more hydrogen on the surface, this hydrogen can no longer screen the potential drop that we have here by applying, putting more electrons here. What will happen if we create a dipole? This will mean that we create kind of a counter field, so something which can screen better. And this is, so there seems to be kind of a maximum coverage that allows us to screen applied potential that we have here. And what happens afterwards is that a hydrogen would desorb in order to separate the charge and therefore have a bigger potential drop. And this is what we also see in our calculations. So approximately after 20 picoseconds of run, where we have the hydrogen, the surface covered with hydrogen, we do see that one hydrogen or proton desorbs and forms a hydronium ion, which is in the vicinity of the surface. And this then changes the potential drop, and we start kind of building up a double layer. So we found this quite interesting to see, usually you see this kind of, change in the potential, but actually how it is built up, this was quite nice. And yes, we do see here also more hydrogen for a certain time, but afterwards we do see desorption. We also see, I'm not showing it here, we do see also occupation of hollow and top sides, and this is interchangeable. Now, let us try to understand this a little bit better. So what is the role of water and how do we understand this potential? In theory, in principle, it's nice that we can decompose our potential drop into three parts. So one is hydrogen coming from hydrogen adsorbed on the surface. So this will be just hydrogen at the surface. This will be something that is also present when the surface is in vacuum and we don't have water. Then there is one part that comes, there are a certain amount of water molecules that are adsorbed on the surface, and then they interact with the surface, and there is a certain amount of charge transfer. I'll show how this happens. And then there are water molecules that are close to the surface which can reorient in order to screen the potential drop. So this will be the third contribution. So this kind of reorientation of water and electronic transfer of water contributions, they are only present in aqueous environment. And if we calculate this, these are the three contributions shown in different colors, then we can analyze what comes where. Now let's first focus on the one that comes from hydrogen adsorption to the surface that is also present in vacuum. And if I put this contribution into my plot, you see that it very closely follows what we have for the vacuum environment. So this kind of adsorption of hydrogen to the surface is very similar whether we are in aqueous environment or whether we are in the vacuum environment. Then the other two contributions that are related to water are on one side this adsorption of water on the surface and then the reorientation of water. If one looked at this chemisorbed water, we see how it changes, as a function of the water coverage. We see that we have a linear behavior, which would mean that any water molecule that is adsorbed to the surface will contribute the same kind of electronic charge to the surface. What we also see that as we increase the coverage of hydrogen on the surface, the coverage of the water, the average coverage of the water molecules goes down. So eventually when we go to 1 monolayer coverage of hydrogen, we don't have any water absorbed on the surface. I should also mention that this water is not like water comes to the surface and stays there. It's not like it's a chemical bond, but it is not so strong. So it's really a dynamic behavior. We do see that water molecules absorb, and then they also desorb and kind of go up and down. But on average, we always have a coverage of 2/3 of a monolayer of water when we are at we have only water with a pristine surface together. What you can also see if you look at these two curves, that up to about half a monolayer of coverage, they're having almost opposite behavior. So they would cancel out, but they will give rise to a shift. And this is the shift that we saw initially in our work function plot. After half a monolayer, we see that the contribution that comes from electrons transferred to the surface continues to raise, but the orientation of water has now a different behavior. So just by reorienting water molecules, we can no longer counteract this kind of contribution. And this is why after approximately half a monolayer, we don't have now just the behavior like we have it at the surface, which is shifted, but these contributions from water play and kind of start to be visible. And this is why we have a change in the structure. So at low hydrogen coverage, the net water impact is small. And when we go to high coverages water, the water impact becomes dominant. Was this somewhat clear? Hopefully. Now let's look a little bit at the chemisorbed water at the surface, because we found this also quite interesting. What we have sketched here is this is a platinum atom on which a water molecule is adsorbed. And what you see here in green and in brownish color, these are the corresponding orbitals that are involved in the bonding. And the conventional picture was that, water absorbs on platinum and it transfers electrons to the platinum it is sitting on. This is, however, not quite true, what we find to our astonishment. So this will be the picture. We have here the platinum D band. We have the oxygen orbitals. We have a bonding and an anti-bonding state. The anti-bonding state is above the Fermi energy. We have some hybridization, and so we have really a transfer of the water from the water molecule to the platinum directly below it, so that we have here a plus and a minus charge. What happens when we look at the surface is actually something different. We see that both the platinum and the water actually lose charge. They give electrons to the surrounding water molecule. So this is a picture if I just have water adsorbed on the surface. The purple color is where an electron will go through, and the yellowish color where the electron is coming from. And you can see that each water molecule that sits on the surface and the platinum below it, because it also loses charge, distributes this electron to platinum atoms that are around it. Now, this has a certain consequence, because this would mean that each water molecule that adsorbs on the surface needs actually a much bigger area than just one atom it is adsorbed on. And therefore, we cannot cover the whole surface with water molecules. And again, this is a dynamic process. Now, the question is, can we, of course, describe something like this also with an implicit solvent, that eventually we would like, to describe the water dynamics and to be able to get these fluctuations in there, but we will need
obviously a certain amount of explicit water molecules still in there, or we must think about clever ways how we can simulate something like this, which at the moment I don't have really a good idea unless I have explicit water.
But
yeah.
I just wanted to say that this is a challenging problem, of course we know, and it's even more challenging because I think that we need to include here a little bit of information also about the electronic structure of the substrate, because it's a combination of contribute coming from interaction of absorbate over the surface, absorbate surface, and water absorbate, and substrate absorbate contribution, which tune the absorption energy essentially over the. With Alexei Kornishev, we are trying to just systematize this for a simple system, one ion on graphene in vacuum, and try to describe this with a model which is very simple, and still we haven't got there. I mean, so it's a challenging problem. So where the absorbate can tune a lot the properties, the substrate can tune a lot the absorption properties and interaction properties of the absorbate.
It depends also, of course, on the adsorbate, because here you saw in what we had for the hydrogen that actually the work function was going down. So we have kind of, as we put more and more hydrogen in the surface, they have kind of a cooperative effect in the vacuum. If you think about something like oxygen, which are repulsive, and or chlorine and so on, then you will have also repulsive interactions, and this will be completely different. Now, water may play a role there. We saw when I discussed the zinc oxide example that water can screen a lot of these unfavorable through space interactions, but what we have through the substrate is, of course, still a contribution. So I think at the moment we focus more on the water side, but we also should not forget that kind of at the interface we do have these effects, and that water, as you say, water substrate interactions are really also something that in principle one should keep in mind.
And it's on both of you. So I think you're completely right. So that's the adsorbate is doing much more than we normally expect. That was also really a surprise for us, because normally the assumption is so that the water, which is chemisorbed, which is transferring, donating part of its electron. But that's not really true. So like Mira was showing, it's really this linear combination of the water orbital plus then that of the underlying platinum atom. So really this linear combination is giving away. So it's really kind of a new complex that's interacting then with the platinum surface. So platinum is really extremely crucial to take into account.
And it's very interesting because this couple platinum water, which is both are of which are positive, these are implications. For instance, when you have an edge, I've also simulated a system with an edge, and the edge is all positive. It's like if, and there is chemisorption of water, all full coverage water chemisorption. So I mean, it's really important. Yeah. I will talk a little bit in October about that.
But again, what you also see that when you start absorbing hydrogen on the surface, that the hydrogen also would like to interact with the platinum. And so in a way, you can imagine that there is a competition between the water and the hydrogen to kind of distribute their charge to the platinum that is around. And obviously, at some point, the hydrogen kind of wins this competition so that the water desorbs. And when you have a completely hydrogen-covered surface, then the surface is like hydrophobic and the water is moving up. So we do see that there is a difference, and you create a hydrophobic gap. And Axel always likes to say that when he first started, simulating platinum with water in there, and I think Dieter Kolb told him that what he is doing is not electrochemistry because there's no hydrogen around. But so there is then, by having the hydrogen adsorbed, then you have this kind of desorption of water. And what you have is basically you don't have the antibonding states that are really empty, but they are partially occupied. So you have
in a way, metallic water, if you want, because you don't have for these molecules a band gap, you have a charge transfer. And so we do have then kind of a revised model that the water molecule transfers charge and the platinum transfer charge to the surrounding platinum atoms at the surface, and you need for each water molecule a much higher area, bigger area where it can absorb simply because it needs to distribute the charge. So we do have bonding that is maybe a little bit more complicated to what we were used when we are just looking, at surfaces in vacuum. Yes, Keith.
I'm just trying to fit this all into a bigger picture view. So you are computing all of this very delicate water and absorbed a proton interaction with the platinum. But also you would like to consider putting a artificial layer of charge sometimes. This is computed charge, right?
Yes, this is...
But you also proposed an artificial layer of charge.
No. So maybe it was confusing with this kind of picture. We were just trying to put it in a picture with... linear combination of atomic orbitals, but no. So Jörg, you want to?
Yeah, so this, let's see, so this artificial charging layer, so this is really on the other side, then it's a complete different boundary. So we don't care about it. It's the other electrode, yeah.
Oh,
so this is
the one you want to ignore. I see.
This is something you want to
all the fun is happening.
Everything, all the fun is actually,
all the fun is here.
and this is everything is completely fine because all the other electrode is doing is transferring the electrons, but this is a real physical charge that we want to describe. So we can really forget to be mature, that we can forget exactly.
Else.
Yeah.
So there's one, two,
yeah.
and the other one.
This is at the money electrode. Okay.
Yes, exactly.
Okay.
So you have the fun electrode, and the other one is completely boring because it's not affecting anything.
Yeah. Sorry.
Okay.
So in a way, what we want to do is to, here we let the system just evolve without applying a bias. If we apply a bias, we can kind of push it in this direction in a way. So experimentalists typically can apply a charge and then they see it's correlated to the coverage. Of course, in a DFT calculation, it is sometimes easier to just put the charge and then see what is change the coverage and then see what is the effect on the potential. So this is the way we went here, but yeah. So this is the working electrode, the money electrode. I like your expression. Yeah. So we talked also about the structures in water and correlations, and I wanted to show you now some of the analysis that we have done here so that one can see it. And what is a very nice thing to look at, the water dipole and how it is oriented with respect to the surface normal or with respect to some other water molecule so that we can see what the rearrangement is. So now this is the system I just described. I have here the platinum. This is the electrode I'm interested in and the surface interface I was discussing. I do have here the water, and in this case, the neon was kind of just confining it. We didn't use it for anything. You do see there is a little bit of structuring on the neon side. Simply, I think this has to do also with our kind of the length of our trajectory, because this is not particularly long. But you do see that on the platinum side, we do have really two kind of peaks that are related to water. And this is, one is the water up, and the one is the water down. So you have to imagine here's the platinum surface, then one is water adsorbed with the oxygen to the surface, and the hydrogens are showing up. And then this is the water down, where on average the hydrogen is pointing towards the surface. Doesn't mean that these are really, again, kind of really fixed. There are still fluctuations, but on average we find many more water molecules that have this orientation close to the surface, and in the second layer many more water molecules that have kind of this orientation. And we can also kind of look, if we look at the density of water, we do see that in this region E, which I again somehow lost my pointer here. So we have on average the bulk water density,
We do have, however, here also fluctuations in the density, so we do have kind of a structuring of the water close to the surface. We do have a little bit of structuring to the neon, but again, this is something that we typically ignore. So it is not important, and it is not influencing our calculation, but we do see important. We always need to make sure that we do have kind of a bulk water region, and what we have here is really true. And again, this here corresponds to the adsorbed water, and we have this kind of bimodal distribution, and we do see, I said that the water is not kind of fixed when it is adsorbed. We do see an exchange of water molecules between these first two layers. Once we have the hydrogen, we do see that the water actually is pushed further away from the surface. Yeah, and minor perturbation in the region C, and this is, again, I mentioned that this is very small as compared to the water dipole. Yes?
May I ask? I just wondering, did you apply any potential?
Not here. We would
Just the
like to
potential
do it. So this was just, we just put different hydrogen as coverages. So here we didn't apply any potential. This is just pristine water. We also have this analysis when we put hydrogen, but so far we didn't. Quite early, we applied some potential when, when we saw the hydrogen evolution on the magnesium. So we were hoping we can see something like this on platinum, but we couldn't see it at the times that we were running it. And so I don't think that we analyzed this in detail. I think that will be interesting to look because of one thing we are not doing when we are just kind of absorbing hydrogen and looking at the how the system reacts, what the potential is. There may be some kind of confinement to some of the water molecules in their movement if we apply a potential. So there I'm not quite sure what will happen, and this will be interesting to look at and compare. Okay, now this is a water solvated in water. And you see, while water may be really moving around and be like an amorphous system, if you look at the solvation of a water molecule, it has also its solvation shell. So what we looked here, if we have two water molecules and you connect the oxygen of this water molecule and then look how the dipole is and where the hydrogens are related. So this is TIP3P water, and this is PBE water. So PBE exchange correlation functional. You see that the PBE water isn't quite so happy. This is overstructured. We found it extremely funny that, this seems to be like happy water. This is, just came out. But you can see the kind of the correlation where the hydrogens are the first shell, then the second shell, and so on. But you do see that there is even water in water. Every water molecule has some structure around it. It's solvation. Up to the second shell, I would say it is pronounced. It becomes then, the further you go, it disappears, and on average, you have something that is amorphous. We also wanted to look what happens if I put iron in water and actually change the charge of the ions. You can do also artificial charging just to see how the water structure evolves. And then we did it at the level of TIP3P water, and we put a sodium. We have this also for a chlorine ion, and then varied the charge of the sodium from 0 to 1, or from the chlorine to -1, and in smaller steps, just to see how the water evolves. Now, what you see here, I think here we start from 0, and here we have sodium +1. What you see, the blue lines are always corresponding to the negative charge in this case, I get the oxygen, then the red ones will be the hydrogen, if I'm not mistaken. Or the red ones are the oxygens, the blue ones are the hydrogens. And you see, so the first two circle will correspond to the first solvation shell. This will be the second solvation shell that you have here, and then you have very faint third solvation shell. And you can see that as we change the charge, here there is, yes, some
reordering simply because we interrupt the hydrogen bonding network. But as we begin to increase the charge, you see that first the first solvation shell becomes really very pronounced, and then also a second solvation shell is built up. And this also relates to what Jörg was showing, when you pull a sodium out of the surface and try to put it into solution, that you start building a solvation shell up, and then first you have a first solvation shell, and then you had a second plateau where the second solvation shell was. And we see it also for the chlorine. And this also relates, to Marcus theory and when an electron transfer happens at what case.
So how do you model the sodium? Is this fully resolved electronically, or is this
This
just like a hard sphere?
This is at the level of, no, this is just a kind of a hard sphere, if you want.
And I'm just curious, what's the time scale for the development of the first and second solvation sphere?
I think it was comparatively quick, but I need to. Actually, we were looking more, to converge the energetics. I'm not sure exactly in order to get really converged results, Jenny ran calculations in the order of 100 of nanoseconds. So it was really very long. But this was to also get the energetics well converged. I think So therefore, I'm not exactly sure how fast it was, but it kind of, we do see that really depending on a charge, which is also not very astonishing because we know that Coulomb interactions are really very important in forming this solvation shell. So here it was kind of nice to see really how going from something that's neutral to something that is fully charged, how the solvation shell appears. And here you see also this kind of radial distribution function plots that are typically shown. So the orange one is corresponding to the sodium-oxygen distance, the blue one to the sodium-hydrogen distance. And you can see when you have a neutral sodium, the two peaks are really overlapping in a sense. So you do have something that is formed because you have an exclusion volume, but they're not separated like you would see. As we start to kind of evolve the charge, when the first solvation shell forms, seen here, you do see that there is a separation of these peaks. And then when you go to the full charge that you would expect on a sodium, you see that you have both the first and the second solvation shells that are completely pronounced there. Jenny went a little bit further to actually analyze the coordination of water, with respect to the sodium, also for the different cases, and try to fit it kind of in different polyhedra by rotating and then seeing. Obviously, we do see here something that is mirrored out, which looks spherical. But of course, if you look at individual snapshots, you always have a certain amount of water molecules that are there. And so if you go to higher charts, so from 2 is probably a bit overdone, but you do see that you have kind of an octahedral arrangement of the water molecules dominating. When you go to somewhat lower charges in between the first and the second solvation shell, you have kind of a dominating kind of pyramidal and bipyramidal arrangements. So just imagine in the middle you have here kind of your sodium, and then these are the water molecules that are coordinated to it. Yeah, and he just looked at the water molecules and then see to what kind of arrangements they are. And of course, if you are running an MD, this will be rotated and so on, so you don't see a pyramid or a bipyramid, but this is in any snapshots that you look, this will be kind of a dominant distribution. Then if you go to negative energies, negative coverages, which for the sodium are probably not so relevant, you have a tetrahedral arrangement, or if you go in a regime where the sodium is really, where did I get it? So when you are in a kind of, I went too fast. Yeah, so if you go to kind of neutral sodium, then you're more kind of in a triangular arrangement.
And so again, he was analyzing the oxygen distance and the angle. And also we have the distributions of the angles, but I thought this will go too far. Yes?
Does the radius of the ion matter?
This was like
It's just the electric field strength.
I think the radius matters in so much and that it kind of really disturbs the hydrogen bonding network that the water would have. And this is also why some ions that are bigger, like iodine and so on, would like to go to a surface because the network is already disturbed, so it doesn't, if you put something in there, it wouldn't perturb the structure of water quite so much. But if you have something like lithium, which is small, people even speculate that lithium doesn't shed completely its first solvation shell when it absorbs on the surface. Again, I haven't looked at lithium. This is something that kind of, let's say, I know from literature that is there. But I think the size matters in as much as how much it disturbs the water structure, probably. Okay, and I think with this, I'm at the end of what I wanted to discuss today. Thank you very much for the attention, for the questions.